Introduction. Good morning, teacher. Good morning, students. Today we will learn chemical reactions of alcohols, phenols, and ethers. Sir, what is chemical reaction? A chemical change is a process where one or more substances are altered into one or more new and different substances. Let's have a demonstration. When we drop bromine in alcohol, then chemical reaction occurs and it forms alkyl halide and water. In this lesson, we will learn more about chemical reactions of alcohols, phenols, and ethers. Objectives. At the end of this lesson, you will be able to explain the chemical reactions of alcohols and phenols, describe some commercially important alcohols, explain preparation, physical and chemical properties of ethers. Chemical reactions. Alcohols can react as nucleophiles as well as electrophiles. When alcohol reacts as nucleophile, then OH bond break. When alcohol reacts as electrophile, then CO bond break. Protonated alcohols react in this way. The disadvantage of using a protonated alcohol is that a strongly acidic solution is required to protonate the alcohol. On the basis of the cleavage of the OH and CO bond, the reactions of the alcohols and phenols is divided into two groups. Reactions involving cleavage of OH bond, acidity of alcohols and phenols. Reaction with metals. Alcohols and phenols react with lithium, sodium, potassium, and other active metals to liberate hydrogen and form metal alkoxides. Phenol reacts with sodium to form sodium phenoxide and liberate hydrogen gas. Phenols also react with aqueous sodium hydroxide and form sodium phenoxide. The discussed reactions show that alcohols and phenols are acidic in nature. Acidity of alcohols. The acidic character of alcohols is due to the presence of polar nature of OH bond. Alkyl group has electron-releasing inductive effect. Due to plus I effect of alkyl groups, the electron density on oxygen increases, due to which polarity of OH bond decreases, and hence the acid strength decreases. Thus, order of reactivity of alcohols when they behave as acids is primary alcohol, followed by secondary and tertiary alcohol. Alcohols are generally weaker acids than water. The relative acidities of alcohols are affected by the substituents attached to the carbon carrying the hydroxyl group, often by an electronic effect called the inductive effect. For example, the acidity of tert-butyl alcohol is lower as compared to methyl alcohol due to the electron donating effect of 3-methyl group in tert-butyl alcohol. On the other hand, 2,2,2-trifluoroethanol is more acidic than methyl alcohol because of the strong electron withdrawing effect of 3 fluorine atoms in trifluoromethyl group, delocalizing the negative charge on oxygen. Alcohols can also act as Bronsted base because of the presence of unshared pairs of electrons on oxygen. Acidity of phenols. Phenols are stronger acid than alcohols as phenols turn blue litmus red and react with alkalis. However, phenols are weaker acids than carboxylic acids. Therefore, phenols do not decompose carbonates or bicarbonates to evolve carbon dioxide gas. Phenols exist as resonance hybrid. As a result of resonance, oxygen atom acquires a partial positive charge. It weakens the OH bond and thus facilitates the release of proton. The phenoxide ion is also resonance stabilized. But phenoxide ion is better stabilized than phenol because in phenol, three contributing structures that are second, third, and fourth involve charge separation, whereas in case of phenoxide ion, there is no charge separation. Hence, phenol has greater tendency to change into more stable phenoxide ion by releasing a proton. On the other hand, in case of alcohols, neither alcohol nor alkoxide ion is resonance stabilized. Thus, alcohols have negligible tendency to form alkoxide ion by releasing a proton. Effect of substituents on the acidity of phenol. Electron-donating groups which destabilize the phenoxide ion by intensifying the negative charge decrease the acidic strength of phenol. Electron-withdrawing groups which stabilize the phenoxide ion increase the acidic strength of phenol. Greater the number of electron-withdrawing groups at ortho and para position, more is the acidic character of phenol. For example, nitro group is electron-withdrawing and thus increase the acidic character. A nitro group at ortho and para positions greatly stabilize the phenoxide ion by permitting a position of the negative charge to be carried by two oxygen atoms. Chemical reactions. Esterification. Alcohol reacts with carboxylic acid, acid chlorides, and acid anhydrides to form esters. Isopropyl alcohol reacts with acetic acid in the presence of sulfuric acid to form isopropyl acetate and water. Alcohol reacts with acid chloride in the presence of pyridine to form ester and hydrochloric acid. Methanol reacts with acid anhydride in the presence of sulfuric acid to form an ester and a carboxylic acid. Phenol reacts with acid chlorides and acid anhydrides to form esters. Phenols do not easily undergo the esterification reaction with carboxylic acids because the reaction is endothermic. Phenol reacts with acetyl chloride in the presence of pyridine to form phenyl acetate and hydrochloric acid. Ethanoic anhydride reacts with phenol in the presence of sulfuric acid to form phenyl ethanoate and acetic acid. The reaction of phenols and alcohols with acetic anhydride in the presence of pyridine is known as acetylation. Acetylation of salicylic acid produces aspirin. Acetic anhydride reacts with salicylic acid in the presence of sulfuric acid to form acetylsalicylic acid or aspirin and acetic acid. Reactions involving cleavage of carbon-oxygen bond in alcohols. Reaction with hydrogen halides. Alcohols, when treated with halogen acids, get converted into halolcanes. When hydrochloric acid gas is passed through ethanol in the presence of anhydrous zinc chloride, it forms chloroethane and water. This reaction does not occur with phenols. Reaction with phosphorus trihalides. Phosphorus halides react with alcohols to form halolcanes. Phosphorus trichloride reacts with ethanol to form chloroethane and phosphorus acid. Dehydration. When alcohols are heated with acids like sulfuric acid, phosphoric acid, or boric acid, they get dehydrated. At high temperature and high acid concentration, alkenes are formed. Dilute sulfuric acid is used for dehydration of secondary and tertiary alcohols to avoid polymerization of alkenes. Ease of dehydration of alcohols is in the order tertiary alcohol followed by secondary alcohol and then primary alcohol. Mechanism. The mechanism of dehydration of alcohols involves the following steps. Step 1. Protonation of alcohol. Due to the presence of lone pair of electrons on oxygen, alcohols act as weak bases and therefore accept proton from acids to form oxonium salts. Step 2. The presence of a positive charge on the highly electronegative oxygen atom weakens the CO bond. As a result, the protonated alcohols readily eliminate a water molecule to form carbocation. This is slow step and therefore rate determining step of the reaction. Step 3. The carbocation formed is reactive species, hence readily loses a proton to form an alkene. Oxidation. In the oxidation of alcohols, hydrogen is removed from the carbon atom bearing OH group and from oxygen of OH group. These reactions are, therefore, also called dehydrogenation reactions. A primary alcohol on oxidation gives an aldehyde, which on further oxidation gives an acid, all containing same number of carbon atoms. Secondary alcohols on oxidation first give ketones with same number of carbon atoms as alcohol. Ketones are further oxidized to give carboxylic acids containing lesser number of carbon atoms. Tertiary alcohols fail to undergo oxidation in neutral or alkaline solution. Action of hot reduced copper. When vapors of primary, secondary or tertiary alcohols are passed over hot reduced copper at 573 Kelvin, different products are obtained. A primary alcohol is dehydrogenated or oxidized to an aldehyde. A secondary alcohol gives a keton. Tertiary alcohols, however, undergo dehydration to give alkenes. Reactions of phenols. Electrophilic aromatic substitution. Phenols are potentially very reactive towards electrophilic aromatic substitution. This is because the hydroxy group is a strongly activating ortho-para-directing substituent. Nitration. With dilute nitric acid at 25 degrees Celsius, phenol gives mixture of ortho and para isomers of mononitrophenols. On adding dilute nitric acid into phenol at 25 degrees Celsius, it forms orthonitrophenol and paranitrophenol. Orthonitrophenol undergoes intramolecular hydrogen bonding, while paranitrophenol undergoes intermolecular hydrogen bonding. Orthonitrophenol is stream volatile, whereas paranitrophenol is less volatile due to the association of molecules and so can be separated by distillation. By treating phenol with concentrated nitric acid, it is converted into 2,4,6-trinitrophenol, that is commonly called as picric acid. Phenol is converted into picric acid by treating it with concentrated nitric acid. Halogenation. Phenols react with halogens in the presence of less polar solvents like carbon disulfide, chloroform, and carbon tetrachloride to give ortho and para isomers of monohalophenols. Bromine in carbon disulfide reacts with phenol and forms 2-bromophenol and 4-bromophenol. Phenols, when treated with bromine water, give polyhalogen derivatives in which all the hydrogen atoms present at the ortho and para positions with respect to hydroxyl group are replaced by bromine atoms. Phenols react with bromine water to form 2,4,6-tribromophenol. Kolbe's reaction. Salicylic acid is formed by the reaction of sodium phenoxide with carbon dioxide under pressure at 400 Kelvin, followed by acidification of product. It is used to prepare aspirin. This reaction is known as Kolbe's reaction. Remer-Tiemann reaction. It involves treatment of phenol with chloroform in the presence of sodium hydroxide at 340 Kelvin, followed by hydrolysis to give salicylaldehyde as a major product. Reaction of phenol with zinc dust. Phenol can be converted to benzene by heating it with zinc dust. Oxidation. When phenol is oxidized with chromic acid, it produces unsaturated conjugated dicaton known as benzoquinone. Some commercially important alcohols. Methanol. Methanol, also called methyl alcohol, was originally produced by the destructive distillation of wood chips in the absence of air. This source led to the name wood alcohol. Today, most of the methanol is synthesized by a catalytic reaction of carbon monoxide with hydrogen. This reaction uses high temperatures and pressures. Properties. It is a colorless, inflammable liquid. Miscible with water in all proportions. It is poisonous in nature. When consumed, causes blindness and even death. Uses. As a solvent for paints, varnishes, and celluloid. For denaturing industrial alcohol, that is to make it unfit for human consumption. As an antifreeze in automobile radiators. Some commercially important alcohols. Ethanol. Ethanol is obtained commercially by fermentation of molasses, which contains sucrose. The sugar in molasses is converted into glucose and fructose by the action of an enzyme that is invertase. Now, the produced glucose and fructose undergo fermentation in the presence of enzyme zymase and produce ethanol and release carbon dioxide. Properties. Ethanol is a colorless, volatile liquid with pleasing smell and burning taste, miscible with water in all proportions. Uses. As an antiseptic in the form of rectified spirit, as an antifreeze in the radiator of automobiles, in spirit lamps, stoves, thermometers, and spirit level. Ethers. Preparation of ethers. By dehydration of alcohols. Alcohols are dehydrated to ethers in presence of concentrated sulfuric acid at 413 Kelvin. The reaction involves the removal of one molecule of water from 2 moles of alcohols. The synthesis of ether is a nucleophilic bimolecular reaction as given below. This method is suitable to prepare ethers having primary groups only. Dehydration of secondary and tertiary alcohols to give corresponding ethers is unsuccessful. Williamson synthesis. When alkyl halide reacts with sodium alkoxide, ethers are formed. Bromomethane is mixed in sodium phenate and it gives methoxybenzene and sodium bromide. Phenols can also be converted into ethers as given below. On mixing sodium hydroxide into phenol, it forms sodium phenoxide. Then, on adding chloromethane, it forms anisole and sodium chloride. Physical properties. Lower members such as dimethyl ether and diethyl ether are gases, while higher members are colorless, pleasurable smelling, low boiling volatile liquids. The solubility of ethers is comparable to those of corresponding alcohols. The solubility of ethers is due to the capability of oxygen molecules to form hydrogen bond with water molecules. The boiling points of ethers are much lower than that of alcohols due to lack of hydrogen bonding. Lower ethers act as anesthetics. Ethers are polar molecules and have definite dipole moments. Chemical reactions. Cleavage of CO bond in ethers. Ethers can be cleaved by using hydroiodic acid or hydrobromic acid to give alkyl halide and alcohol. Hydroiodic acid reacts with diethyl ether and it forms ethanol and ethyl iodide. With excess of hydroiodic acid, alcohol formed further reacts to form ethyl iodide. Overall reaction is hydroiodic acid reacts with diethyl ether at 373 Kelvin and it forms ethyl iodide and water. The order of reactivity of halogen acids is in the order hydrogen iodide followed by hydrogen bromide and then hydrogen chloride. Mechanism of cleavage by HI. The various steps involved are dissociation of HI, protonation of ether, nucleophilic attack by iodide ion on the protonated ether resulting in the formation of alcohol and alkyl halide. The alkyl oxygen bond in alkyl aryl ethers can be cleaved by hydrogen halides to form phenol and alkyl halides. Electrophilic substitution. The alkoxy group attached to aromatic ring activates the ring towards electrophilic substitution and directs the incoming electrophile to ortho and para positions. Halogenation. Phenylalkyl ethers undergo halogenation in the benzene ring. Thus, anisole exhibit bromination with bromine in acetic acid even in the presence of iron 3-bromide catalyst. Para-isomer is obtained in 90% yield. Friedel-Crafts reaction. Both alkyl and acyl groups are introduced at ortho and para positions by reaction with alkyl halide, that is Friedel-Crafts alkylation, and acyl halide, that is Friedel-Crafts acylation in the presence of a Lewis acid catalyst like anhydrous aluminium chloride. Methyl chloride reacts with anisole in the presence of anhydrous aluminium chloride and carbon disulfide and forms 2-methoxytoluene and paramethoxytoluene. Acetyl chloride reacts with anisole in the presence of anhydrous aluminium chloride and forms 2-methoxyacetophenone and 4-methoxyacetophenone. Nitration. The reaction of anisole with a mixture of concentrated sulfuric acid and concentrated nitric acid forms a mixture of ortho and para-nitroanisole. Did you know? Ethers can be used as external cleansing agent, used as a solvent, and in the extraction of oils, fats, waxes, resins, and alkaloids. Methanol is also a high-octane, clean-burning fuel that is a potentially important substitute for gasoline in automotive vehicles. Summary. Let us summarize what we have learned. Alcohols and phenols react with lithium, sodium, potassium, and other active metals to liberate hydrogen and form metal alkoxides. The acidic character of alcohols is due to the presence of polar nature of OH bond. Phenols are stronger acid than alcohols. Alcohol reacts with carboxylic acid, acid chlorides, and acid anhydrides to form esters. Phenol reacts with acid chlorides and acid anhydrides to form esters. Alcohols, when treated with halogen acids, get converted into halolcanes. When alcohols are heated with acids like sulfuric acid, phosphoric acid, or boric acid, they get dehydrated. Phenols react with halogens in the presence of less polar solvents like carbon disulfide, chloroform, and carbon tetrachloride to give ortho and para isomers of monohalophenols. Salicylic acid is used to prepare aspirin. Most of the methanol is synthesized by a catalytic reaction of carbon monoxide with hydrogen. Ethanol is obtained commercially by fermentation of molasses, which contains sucrose. Alcohols are dehydrated to ethers in presence of concentrated sulfuric acid at 413 Kelvin. Ethers can be cleaved by using hydroiodic acid or hydrobromic acid to give alkyl halide and alcohol.